Hello, in this video we're going to review some advanced integration techniques. For our first problem, we have the integral from 0 to 3 of 1 over the square root of 9 plus x squared dx. Now this is in the form of 1 over the square root of a squared plus u squared, where a is our constant term, u is our variable term. And if we think of it in this form, then a is 3 and u is x. So when we have something in this form of a squared plus u squared, we can integrate using trig substitution, or at least we can try to integrate using trig substitution. And the substitution we want to make here is u equals a tan theta. So our u is just x in this problem. So we'll have x equals, and our a is 3, so x equals 3 tan theta. And if x equals 3 tan theta, then dx equals 3 secant squared theta d theta. So now I can substitute 3 tan theta in for x. I can substitute 3 secant squared theta d theta in for dx. Notice that in our expression we have x squared. So I'm just going to go ahead and write down what x squared is equal to here. If x is 3 tan theta, then x squared, we're just squaring both sides of this equation, is 9 tangent squared theta. And we have more than just x squared. We have 9 plus x squared. So I'm going to go ahead and try and get a match before I make my substitution. So I'm going to add 9 to both sides of this equation. And that'll give me 9 plus x squared equals 9 plus 9 tangent squared theta. I can factor a 9 out of that expression. So I get 9 times 1 plus tangent squared theta. And 1 plus tangent squared theta is secant squared theta. So I get 9 secant squared theta. So I can substitute that in for the 9 plus x squared. Now we actually have the square root of 9 plus x squared. The square root of 9 plus x squared, and I'm just going to take the square root of both sides of this equation, would be the square root of 9 secant squared theta, and the square root of 9 secant squared theta is 3 secant theta. Okay, then we have 1 over that, 1 over the square root of 9 plus x squared. So 1 over the square root of 9 plus x squared is 1 over 3 secant theta. So let's go ahead and rewrite our integral now. I'm going to replace 1 over the square root of 9 plus x squared with 1 over 3 secant theta. And then I'm also going to have to replace the dx with 3 secant squared theta d theta. Now when I rewrite my integral, I can't use the 0 and the 3 because those are x values. In a dx problem, we know that these bounds are x values. So I'm going to go ahead and convert these x values into theta values so I can have correct bounds on my new integral. So we've got our lower bound x equals 0. And to convert that, I'm just going back to my equation that relates x and theta. When x is 0, that equation becomes 0 equals 3 times tan theta. Divide both sides by 3, we get 0 equals tan theta, and tan theta equals 0 at 0, so theta equals 0. When x equals 0, theta equals 0. So in my new integral, my lower bound is going to be theta equals 0. And then we'll convert the upper bound. When x equals 3, my equation becomes 3 equals 3 tan theta. Divide both sides by 3, we get 1 equals tan theta. And I know the tangent of pi over 4 equals 1. So theta equals pi over 4 is my upper bound. Now we need 1 over the square root of 9 plus x squared, and that's equal to 1 over 3 secant theta times dx, and dx equals 3 secant squared theta d theta. Now we can simplify. 3 over 3 is 1. Secant squared theta over secant theta is just secant theta. So I have the integral from 0 to pi over 4 of secant theta d theta. Now secant theta is not an easy one to integrate. In order to integrate secant theta, we're going to use kind of an algebra trick here. We're going to multiply by a fancy form of 1. We're going to multiply by secant theta plus tangent theta over secant theta plus tangent theta. Okay, so I'm going to distribute secant theta, just the secant theta. I'm going to distribute, and then my integral becomes integral from 0 to pi over 4 secant squared theta plus secant theta tangent theta over secant theta plus tangent theta. And then we'll put the d theta at the end. We'll multiply that at the end. The derivative of my denominator happens to be my numerator. The derivative of secant theta is secant theta tangent theta. The derivative of tangent theta is secant squared theta. So the derivative of the denominator is equal to the numerator. That means I can do a U-substitution here, letting the denominator equal u. So if u equals secant theta plus tangent theta, du equals secant theta tangent theta plus secant squared theta d theta. And now my integral becomes, and I can't use 0 and pi over 4 because those are theta values, not u values. So I'm just going to use an alpha and a beta for the time being. So this integral just becomes 1 over u times du. And that integrates to the natural log of the absolute value of u from alpha to beta. And then we'll come out of that and convert the u back in terms of theta. So it's the natural log of the absolute value of secant theta plus tangent theta. And now that we're back in terms of theta, we can use our 0 and our pi over 4, which were theta values. Okay, so we want to substitute pi over 4 in for theta. And that's going to give us natural log of the absolute value. The secant of pi over 4 is reciprocal of cosine pi over 4, and cosine of pi over 4 is 1 over root 2. So the reciprocal of that is root 2. Plus, the tangent of pi over 4 is 1. Okay, and since root 2 plus 1 is positive, we don't need the absolute value there. We can go to parentheses. And we want to subtract then. When we substitute in our 0, we're just going to get the natural log of the absolute value. The secant of 0 is 1 plus the tangent of 0 is 0. So that's the natural log of 1, and the natural log of 1 is 0, so that drops out. And our final answer is natural log of square root of 2 plus 1. Number 2, we're integrating the square root of 9 minus x squared dx from 0 to 3. This is in the form of a squared minus u squared. So for a squared minus u squared, we can do a trig substitution, letting a equal 3 and u equal x. Okay, when it's in the form of a squared minus u squared, we're going to do a sign substitution. So we've got x equals 3 sine theta. If x equals 3 sine theta, then dx equals 3 cosine theta d theta. And x squared, if I square both sides of this equation, x squared equals 9 sine squared theta. 9 minus x squared. Again, I'm trying to get a match with the expression I have over here. 9 minus x squared would be 9 minus 9 sine squared theta. And if we factor out a 9, we're left with 1 minus sine squared theta, which is cosine squared theta. And we've got the square root of 9 minus x squared in our integral. So the square root of 9 minus x squared is the square root of 9 cosine squared theta, which is 3 cosine theta. So I can substitute 3 cosine theta in for the square root of 9 minus x squared, and I can substitute 3 cosine theta d theta in for the dx. And then our integral becomes, and it's a definite integral, so once again, we have to convert our bounds, or we can just wait until the end after we've rewritten the problem in terms of x and use the 0 and the 3. But I'm going to go ahead and convert now. So when x equals 0, I'm looking at this equation that relates x and theta to convert my bounds. When x equals 0, the equation becomes 0 equals 3 times the sine of theta. Divide both sides by 3, we get sine of theta equals 0, and that occurs when theta equals 0. So x equals 0 corresponds to theta equals 0. Now when x equals 3, we have the equation 3 equals 3 sine theta. Divide both sides by 3, we get 1 equals sine theta, and theta equals pi over 2. So when x is 3, theta equals pi over 2. Then our new integral becomes integral from theta equals 0 to theta equals pi over 2. If the square root of 9 minus x squared just was equal to 3 cosine theta, and then dx is equal to 3 cosine theta d theta. So I have 9 cosine squared theta. The 9 is a constant multiple. I'm going to bring that outside of the integral. So I have 9 times the integral from 0 to pi over 2 cosine squared theta d theta. In order to integrate cosine squared theta, we're going to use the power reducing formula. Cosine squared theta equals 1 plus the cosine of 2 theta all over 2. The all over 2 I'm going to bring outside and make it 9 over 2. We're integrating from 0 to pi over 2 with respect to theta. Okay, and then this integral becomes theta plus the derivative of sine is cosine, so sine 2 theta, and then we have to divide by 2 to compensate for our U-substitution. That I just kind of did the U-substitution in my head there. From 0 to pi over 2. Now we want to substitute in our upper bound, so that's pi over 2 plus 1/2 times the sine of 2 times pi over 2. 2 times pi over 2 is pi. The sine of pi is 0. So that's just 0. Minus, and then we're subbing in our lower bound, which is going to give us 0 plus 1/2 times the sine of 2 times 0. The sine of 0 is 0. So that's all just 0. And we get 9 over 2 times pi over 2 for a final answer of 9 pi over 4. For number 3, we want to integrate 1 over the square root of x squared minus 9 dx. This is in the form of u squared minus a squared, so we're also going to do a trig substitution here, but we're going to use a secant substitution. Our a is 3, again. Our u is x, again. So we have x equals 3 secant theta. And if x equals 3 secant theta, then dx equals 3 secant theta tangent theta d theta. And x squared equals 9 secant squared theta. I'm going to try and get a match with this expression here. So x squared minus 9 equals 9 secant squared theta minus 9. I can factor out a 9 on the right-hand side. And secant theta minus 1 is tangent squared theta. So the square root of x squared minus 9 equals the square root of 9 tangent squared theta, which equals 3 tan theta. Okay, so in my integral, I can replace the square root of x squared minus 9 with 3 tan theta. Now this one is not a definite integral, so I don't have to do that step where I converted my bounds. I'm ready to go ahead and set up my new integral. So we'll have integral of 1 over 3 tan theta. And then dx gets replaced with 3 secant theta tangent theta d theta. We can simplify. 3 over 3 is 1, so that crosses out. And then tan theta over tan theta is 1. So we're just left with the integral of secant theta d theta. Now we integrated this just a moment ago. Was that number 1 or number 2? By multiplying by secant theta plus tangent theta over secant theta plus tangent theta. And we saw that that gave us the natural log of the absolute value of secant theta plus tangent theta plus c. And we don't want to leave our final answer in terms of theta. We want to convert it back in terms of x. We didn't have to do that with the definite integral because we had theta values that we could substitute into our equation. But here we're going to have to convert back to x. So I'm going to draw a right triangle just to use as reference. I know from this original substitution that x equals 3 secant theta, and that tells me that secant theta equals x over 3, and that tells me that cosine theta equals 3 over x. It's just the reciprocal. So the 3, if my theta is this angle down here, 3 is the adjacent side, x is the hypotenuse. And then using Pythagorean theorem, the other leg is the square root of hypotenuse squared minus leg squared. So square root of x squared minus 9. And then from here I can just read that the secant of theta, well I know the secant of theta. The secant of theta is x over 3 plus, and then the tangent of theta would be the opposite side over the adjacent side. So the square root of x squared minus 9 over 3 plus c. And they have the same denominator. If we like, we can combine that into a single fraction. We've got x plus the square root of x squared minus 9 over 3 plus c. Number 4, we're integrating sine cubed x cosine squared x dx from 0 to pi over 2. Here we have an odd number of sines and an even number of cosines. So we're going to save one of our sines and convert the sine squared to cosine. We're going to save the sine for our du. This is going to be a U-substitution. So I'll save a sine x, and that leaves a sine squared x, cosine squared x, dx. And we're going to convert this sine squared into cosine squared so that we only have one sine x and everything else will be in terms of cosine. Sine squared x is 1 minus cosine squared x times the cosine squared x that's already there, dx. Okay, now I'm going to let u equal cosine x, and that means du equals negative sine x dx. So here's my sine x dx. I need a negative 1, so I'm going to multiply by negative 1 here and multiply by negative 1 here. And now I have negative sine x dx. So that's going to become my du. This right here is going to become my du. We're going to rewrite our integral. But now that it's a U-substitution, I can't use the 0 and the pi over 2. Those are x values. Those are not u values. So let's go ahead and convert our bounds. At x equals 0, I'm using this equation right here to convert my bounds. U equals the cosine of 0. Well, the cosine of 0 is 1, so u equals 1. So here u equals 1. And then at x equals pi over 2, u equals the cosine of pi over 2. The cosine of pi over 2 is 0, so that means u equals 0 up here. Okay, so our new integral goes from u equals 1 to u equals 0. We have a negative out front, and then the negative sine x dx becomes the du. It still leaves us with 1 minus u squared times u squared du. So we'll distribute the u squared to the 1 minus u squared. We get negative integral from 1 to 0, u squared minus u to the 4th du. Okay, we can use power rule here. U cubed over 3 minus u to the 5th over 5 from 1 to 0. And then we sub in our upper bound, which is 0 minus 0, minus, sub in the lower bound, 1/3 minus 1/5. And then the 0 minus 0, that just goes away. So now we have a double negative here, which is going to make it just positive 1/3 minus 1/5. So that's 5 minus 3 over 15, which is 2 over 15. Okay, we want the limit as b approaches infinity. Integral 0 to b, e to the negative 6x dx. So my u will be negative 6x. My du will be negative 6 dx, which means my dx is negative 1 over 6 du. And I'm going to go ahead and convert my bounds, since this is a definite integral. At x equals 0, and I'm looking at this equation here to convert my bounds. At x equals 0, u equals negative 6 times 0 equals 0. So at x equals 0, u equals 0. So u will equal 0. And then at x equals b, we have u equals negative 6 times b. So u equals negative 6 times b. So our new integral, well, we still have the limit as b approaches infinity. Integral from 0 to negative 6b. And then e to the negative 6x becomes e to the u, but my dx becomes negative 1/6 du, negative 1/6 du, like so. Now the constant multiple I can bring outside, so I have negative 1 over 6 times the limit as b approaches infinity of the integral from 0 to negative 6b e to the u du. The integral of e to the u du is just e to the u. So negative 1/6 times the limit as b approaches infinity of e to the u, and I'm going to go ahead and put the negative 6 back in, e to the negative 6x. And because I did that, I don't have to use my u bounds. I can go back to using my x bounds, which are a little cleaner. And it actually is going to end up being the same thing, because here when we sub in b, we get e to the negative 6b. But up here, if I left it in terms of u, when we sub in negative 6b for u, we get exactly the same thing, negative 6, or e to the negative 6b. Okay, so now this is, I'm going to sub in my upper bound. I get e to the negative 6b minus e to the negative 6 times 0. So e to the 0, which is 1. Negative 1/6. Okay, now let's go ahead and try and take this limit. Well, e to the, actually, it's easier to see what's happening with limits if we don't have negative exponents. So let me take one more step to simplify this. E to the negative 6b is 1 over e to the 6 times b. Minus, and then e to the 0 is 1. Okay, so now let's take the limit as b approaches infinity. As b approaches infinity, the denominator is approaching infinity here. E to the 6 times infinity, that's approaching infinity. So 1 over infinity approaches 0. And then this gives me negative 1/6 times 0 minus 1 for a final answer of 1 over 6. Number 6, we want to integrate x e to the root x dx. Now this looks like an integration by parts, but I'm kind of thinking a step ahead here. And if I let u equal x, then my dv is e to the root x dx. And how do we integrate e to the square root of x? So I'm not sure that's gonna work as well as I had hoped. Straight u-sub's not gonna, well, it might be useful. I think we might be able to work with a U-substitution here. Let's try it and see what happens, because I don't think we're ready for integration by parts. If we let u equal square root of x, then I have e to the u, but I also have this extra x over here, and my du is a little messy. Derivative of square root of x is 1 over 2 square root of x dx, which I do not have here. But if I solve this for dx, see, we've got 2 root x du equals dx. I'm just going to see what happens when I start making substitutions. So I want to put this in for dx, and I want to put this in for u. That's going to give me the integral of x e to the u 2 root x du. So we still have to get rid of x root x. Well, the root x is equal to u. So that's x e to the u times 2u du. And if u equals the square root of x, then u squared equals x. If I just come back up here and I square both sides of that equation, I get u squared equals x. So I can replace the x with a u squared. So u squared e to the u 2u du. Let's write that a little bit better. U squared times u is u cubed. E to the u times 2, the 2 can come out front, du. So we went from having x to the power 1 to having u cubed, but this actually looks much better because e to the u is easy to integrate. So now we're in a form where we can do integration by parts much more easily. All right, so we've got 2 times, we're going to do integration by parts. So since I already have u's in my integral here, I'm not going to call my first part u for integration by parts. I'm just going to call it w. Call it w. So w is going to be u cubed. And actually, you know what? We can use tabular method here. Why don't we do that? And then I don't have to worry about what I'm calling it. So tabular method, my polynomial u cubed is what I'm going to take the derivative of, and then the e to the u du becomes my dv. That's what I'm going to integrate. So I have u cubed, 3u squared, 6u, 6, and then 0. We're going to alternate our signs here. So this one's negative, positive, negative. And then I'm going to integrate e to the u, which is just going to give me e to the u every time. So that's nice. Okay, and then we're going to multiply that times that, that times that, that times that. Oh, this is a long one. And that times that. And we still have this 2 hanging out in front as well. We don't want to forget about him. All right, so we have 2 times, and then integration by parts gives us u cubed e to the u minus 3u squared e to the u plus 6u e to the u minus 6e to the u. Well, they all have e to the u in them, so I'm going to go ahead and factor out e to the u. 2e to the u times u cubed minus 3u squared plus 6u minus 6. And we won't leave our final answer in terms of u. We'll write it in terms of x. So e to the u will be e to the square root of x. If u is the square root of x, then u cubed is x root x minus 3u squared is x. U is the square root of x minus 6 plus c. Number 7, we want to integrate x tan squared x dx. Well, we can't do a u sub with that x in front, so this looks like integration by parts. I'm a little hesitant because I don't think it's easy to integrate tan squared x in our integration by parts, but it's manageable. We can do it. So for integration by parts, I'm going to let the u, we could use a tabular method here, but since this is a complicated, tan squared x is complicated to integrate, so I'm not going to do tabular method. U equals x, then my dv equals tan squared x dx. So the derivative of u just equals dx, and then v equals the integral of tangent squared x dx. We can rewrite tangent squared x. The way we integrate tangent squared x is to use the Pythagorean identity and rewrite it as secant squared x minus 1. Secant squared x minus 1 dx, and then we can integrate each one of those terms individually. So the integral of secant squared x is tan x, and the integral of 1 is x. Okay, so now we have what we need. For parts, we want to take our u times our v. So x times tan x minus x minus the integral, and then we want to integrate our du times our v du. So we want to integrate tan x minus x times, and then that's just dx, equals x tan x minus x minus the integral. To integrate tangent x, I'm going to write that as sine x over cosine x. Okay, so x tan x minus x minus, and then to integrate sine x over cosine x, it's a U-substitution. I'm going to go ahead and do that one in my head. The denominator is going to be my u. So if u equals cosine x, then the derivative of that is negative sine x dx. We have sine x dx. This is hard to explain how I'm doing it in my head, so I'm just going to go ahead and write it out. Minus, I'm going to split this into two integrals here. So we'll do minus and then sine x cosine x dx plus, because I have a double negative, integral of x dx. Okay, so now let me try and explain this again, what I was thinking. So if my u is cosine x, then my du is negative sine x dx, and I have the negative out here. So that's going to become part of my du along with the sine x dx. So it'll actually be plus the integral of 1 over u du, which is ln absolute value of u, and my u was cosine x, plus my c. Okay, and then over to the next term, this integrates as x squared over 2, then plus c. Okay, now if I were to distribute my x, I've got a like terms here, the negative x squared we could actually combine with this term here. So let's see if that helps. We have x tan x minus x squared plus the natural log of the absolute value of cosine x plus 1/2 x squared plus c. So the minus x squared and the plus 1/2 x squared is just going to be minus 1/2 x squared. So final answer, x tan x minus 1/2 x squared plus ln absolute value cosine x plus c. Number 8, integral of x cubed ln x dx. Okay, this looks like another integration by parts, and the natural log has priority for our u. U equals ln x, then dv is everything else. That's going to be the x cubed dx. So du is 1 over x dx, and my v, x to the 4th over 4. Okay, so we're going to multiply u times v, which is x to the 4th over 4 ln x minus the integral v du. Okay, so the 1/4 can come out, and then I have 1 over x times x to the power of 4. That's just x cubed dx. All right, so we have x to the 4th over 4 ln x minus 1/4 times, then just power roll, x to the 4th over 4 plus c. So final answer, x to the 4th over 4 ln x minus x to the 4th over 16 plus c. Number 9, integral of x squared sine 2x dx from 0 to pi over 2. This looks like another integration by parts, and I think I can do tabular method. If we're letting our u equal x squared, we would go from x squared to 2x to 2 to 0, and then sine 2x, derivative of cosine is negative sine, so I have negative, and then I have to divide by 2 when I do the u sub, which I did in my head. Okay, then derivative of sine is cosine, so I need the negative to get a match, and then I need to divide by 2, so that's a 1/4. Then one more time, the derivative of cosine is negative sine, the negative's already there, and I need to divide by 2, so 1 over 8. We're going to alternate signs here, and then multiply diagonally down. So we get negative x squared over 2 cosine 2x, and then positive 2 over 4, so 1/2 times x, x over 2, sine 2x, and then plus 2 over 8 is 1/4 cosine 2x plus c. Oh, this is a definite integral, not plus c. We'll evaluate that from 0 to 2 pi. So we'll start with the 2 pi. We have negative 2 pi squared over 2. Cosine of 4 pi is 1 plus 2 pi over 2. Sine of 4 pi is 0 plus 1/4. Cosine of 4 pi is 1 minus, and now we sub in our 0. Negative 0 over 2 times cosine, that's 0, plus 0 over 2, that's 0, plus 1/4 cosine of 0. Cosine of 0 is 1, so that'll look like that. So we have negative 4 pi squared over 2 plus 1/4 minus 1/4, that's 0. So final answer, negative 2 pi squared. Number 10, integral of 1 over x squared times the square root of x squared minus 16 dx. This one looks like probably trig sub, because we've got u squared minus a squared, and that x squared in the denominator, that is not going to help us with a U-substitution. Okay, so a trig sub here would be in the form of secant. Our u is x and our a is 4. So we have x equals 4 secant theta, which means our dx is 4 secant theta tangent theta d theta. And x squared, if I square both sides, I get 16 secant squared theta. I'm trying to match my expression over here. So x squared minus 16 would be secant, or 16 secant squared theta minus 16. And then I factor out a 16. And secant squared theta minus 1 becomes tangent squared theta. So 16 tangent squared theta. And then I'm going to take the square root of that and get 4 tan theta. So I can replace the square root of x squared minus 16 with 4 tan theta. And the x squared, that extra x squared in front here, we can use 16 secant squared theta. And then our dx, of course, 4 secant theta tan theta. Whew, this is a big one. All right, so 1 over a lot. X squared is 16 secant squared theta. And then the square root of x squared minus 16 is 4 tan theta. And then the dx is 4, let me just write it in the numerator instead of out to the side. The dx is 4 secant theta tangent theta d theta. Okay, so we can cancel out a tan theta. We can cancel out the secant theta in the numerator and one of the secants in the denominator. Cancel out the 4 in the numerator and the denominator. This is looking pretty good. And that's just going to leave me with 1 over 16 integral 1 over secant theta d theta. And that becomes just cosine theta. 1 over secant theta is cosine theta, which is very easy to integrate. So 1 over 16 sine theta plus c. Oh, no, we're not done because that's a theta. We've got more to do. Okay, let's draw our right triangle. We know from our original substitution equation here that secant theta equals x over 4, which tells me that cosine theta equals 4 over x. So if I put theta here, the 4 goes here, the x goes here, and the other leg is hypotenuse squared minus leg squared. Okay, so 1 over 16, the sine of theta is opposite over hypotenuse, so square root of x squared minus 16 over the hypotenuse x plus c. There we go. Number 11, we're integrating 1 over the quantity x squared plus 2x plus 2 squared dx. Okay, so options here, we could try and multiply the denominator. At first I thought maybe complete the square. Well, actually x squared plus 2x plus 1 looks like it's factorable. So maybe, yeah, let's try that first. 1 over, I believe, I'll do a quick multiply it back out to make sure. Is that right? X squared plus 2x plus 1. Oh no, that's not how that factors. That's very sad. Okay. Well, we might be completing the square inside of the square. That's the only thing I can think to do at this point. Let's see what we get. All right, so we have, I have this whole thing like squared right here, which is throwing me off a little bit, but just in the parentheses, we can complete the square of what's in there. So that's going to be x squared plus 2x plus 1 is what would complete this square. And I have a 2, so the 2 I can just break into 1 plus 1 like that. And then that's going to become x plus 1 squared. So that's my x squared plus 2x plus 1. But then I still have another plus 1, and all of that is squared. Okay, so that's a little weird. I'm not used to seeing it like this, but we can think of this as u squared plus, and then a squared. So unfortunately, this looks like another trig sub. We can say x plus 1 equals tan theta, since it's in the form of u squared plus a squared. Okay, then our dx equals secant squared theta d theta, and x plus 1 squared equals tan squared theta, x squared plus, or x plus 1 squared plus 1 equals tan squared theta plus 1. And then if we take this whole left-hand side and square it, and this whole right-hand side and square it, we see that x plus 1 squared plus 1 all squared is just equal to secant squared theta squared, or secant to the 4th theta. Okay, so let's rewrite our integral now. It's the integral of 1 over, and my whole denominator there is just secant to the 4th theta. My dx is secant squared theta d theta. Secant squared over secant to the 4th is 1 over secant squared theta. And the reciprocal of secant is cosine, so that's cosine squared theta. And we integrate cosine squared theta using the power reducing formula. So it's 1 plus cosine of 2 theta over 2. The 2 can come out, so 1/2, and then the integral of 1 is theta, and the integral of cosine 2 theta is sine 2 theta times 1/2. And this is not definite, so just r plus c at the end, but we need to get our answer in terms of x. So let's draw our triangle. And here's our equation. Tan theta equals x plus 1. So x plus 1 over 1 is the tangent of theta. And the hypotenuse is leg squared plus leg squared, which is what we had in our original expression, so that's looking good. And our answer is going to be 1/2. Now theta, just theta by itself, we need to express either in terms of arctangent or arcsine, something like that. I mean, it's kind of your choice. I'm going to go with arctangent. And I guess I'll go ahead and distribute my 1/2 while I'm at it. So 1/2 arctan x plus 1 plus 1/4. Oh, the sine of 2 theta. So that's problematic because my triangle, the angle in my triangle is theta, not 2 theta. So I can't do opposite over adjacent. I have to rewrite sine of 2 theta. I didn't notice that. Okay, sine of 2 theta here is equal to 2 sine theta cosine theta. We have to rewrite it in terms of theta, or we can't use our triangle to convert our answer back in terms of x. So now that's times 2 times the sine of theta. The sine of theta is opposite over hypotenuse. And the 1 plus x plus 1 squared is the same as x squared plus 2x plus 2. I'm going to write it that way to save myself some parentheses. Okay, so that's sine theta, and then we have to multiply that by the cosine of theta, and the cosine of theta is 1 over, oh gosh, that same denominator, x squared plus 2x plus 2. Alrighty, plus c. We got it. Okay, so let's clean that up a little bit. 1/2 arctan x plus 1 plus, so the 1/4 times 2 is 1/2. It's going to put the 2 in the denominator. And really I just have the x plus 1 in the numerator. And in the denominator I have square root of stuff times square root of stuff. So that's just the stuff. X squared plus 2x plus 2. And I forgot my 1/2. That's, wait, nope, not like that. The 2 on the bottom would be like this. I probably should distribute the 2, but I am out of room, so we are going to stop there. Number 12, the integral of ln x over x to the 4th dx from 1 to infinity. Okay, this one looks like integration by parts, and ln x has priority for our u. So if u equals ln x, then dv has to be 1 over x to the 4th dx. So du, 1 over x dx, and v, if we integrate 1 over x to the 4th, we get x to the -3 over -3. U times v, -1 over 3x cubed times ln x minus the integral, and we need v du. So it's 1 over x times -1 over 3x cubed. Well, the times -1 over 3 I can bring out, so plus 1/3. And then that's going to be 1 over x to the 4th, or x to the -4 dx. So negative ln x over 3x cubed plus 1/3 times x to the -3 over -3. And this is a definite integral, so, well, let me simplify this a little bit, make it look better. Negative ln x over 3x cubed minus 1 over 9x cubed. Okay, so this is, we still have to evaluate this from 1 to infinity. We're going to use a limit to do that. So we'll take the limit as b approaches infinity of this, and now both of these terms are negative. I'm going to go ahead and factor out a -1, and I can bring that right out in front of the limit, so that I have ln x over 3x cubed plus 1 over 9x cubed. And they almost have a common denominator, not quite. If I just multiply this one by 3 over 3, they would. So I'm going to do that. Negative limit as b approaches infinity, 3 ln x plus 1 over 9x cubed from 1 to b. From 1 to b. So I'm going to sub in the b. So negative limit b approaches infinity of 3 ln b plus 1 over 9b cubed minus 3 ln 1 plus 1 over 9 equals negative. Okay, so let's look at the limit now. If b is approaching infinity, this first term is going to approach 0 because the numerator is logarithmic, and that grows much slower than the denominator. The denominator is power function. It's growing faster than the numerator, so that's just going to approach 0. So 0 minus. And then as b is approaching it, well, no, there's no b over here. So this is just 3 times the natural log of 1. Natural log of 1 is 0. So 0 plus 1 over 9. Yeah, so it's just negative 1/9, or 1 over 9. 13, the integral of cosine x over 4 plus sine squared x dx. We have an odd number of cosines and an even number of sines. So it looks like we want our cosine, save that cosine up there for a du. We can let u equals sine x, du equals cosine x dx. So this is just a pretty straightforward U-substitution. We get the integral of 1 over 4 plus u squared du. Oh, I spoke too soon. Yeah, it's a simple U-substitution, but then we have to deal with how do you integrate 1 over 4 plus u squared. Now you could, don't immediately think trig substitution. We could do a trig substitution, but it would be more work than is necessary if you recognize that this is 1 over a squared plus u squared du, which integrates to 1 over a arctan u over a plus c. Our a is 2 and our u is u. So this is going to be 1/2 arctan u over 2 plus c. Now we don't want to leave u in our final answer. U is equal to sine of x. Oh, that's a little odd. We've got arctan of sine, but that can happen. 1/2 arctan of the sine of x over 2 plus c. 14, we want to integrate 1 over 9x squared plus 6x plus 10 dx from negative infinity to infinity. Okay, so we may end up having to complete the square here, but if this is factorable, it would be nice if we could do partial fractions instead. So let's try. 9 could be 1 and 9 or 3 and 3. I'm feeling 3 and 3. I'm really just doing guess and check at the moment. And then 10 could be 2 and 5 or 1 and 10. It's not 1 and 10 because 30 and 3 is not going to give me 6. So it could be 2 and 5. That would be 15 and 6. Nope, 15 and 6 is not going to work. So I'm thinking this one is not factorable. That's unfortunate. In that case, we shall complete the square and hope for the best. Okay, so 1 over, I'm going to factor out a 9. 6 over 9 is 2 over 3. And we want half of the middle term, which is 1/3, and we would square that and get 1/9. Oh, that's not too bad, because then we multiply that by the 9. When we distribute the 9, our 1/9 really is just a 1. And so I had a plus 10, which I can break apart into 1 plus 9. And now we have this. Okay, so 1 over 9 times x plus 1/3 squared plus 9. I can factor out a 9 there and bring it entirely out of the integral. So I would have 1/9 integral negative infinity to infinity 1 over x plus 1/3 squared plus 1 dx. Now this is looking like a trig sub. Actually, we don't need trig sub because we have a 1 on top and we've got a 1 down here. No other x's or anything. This is just an arctan. This is in the form of 1 over u squared plus 1. So that's an arctan. That integrates to 1 over 1, arctan x plus 1/3 over 1. So I've got my 1/9 hanging out in front, and And, then we have this, our integral is going to be 1 arctan x plus 1/3. And then we're going from negative infinity to infinity, which, we're not allowed to do. This is an improper integral. So we need to take a limit. Well, but see, the problem is we have an A and a B. So we need two different limits. We got to split this one up. Okay, so we're going to do 1/9. We're going to go let's go from negative infinity to 0. 0 shouldn't be a problem. We'll go from negative infinity to 0, and then from 0 to infinity. So we'll let A approach negative infinity, and we're going to do arctan x plus 1/3 from A to 0 plus, and then we'll have the limit as B approaches infinity for arctan x plus 1/3 0 to B. Okay, so we need to evaluate both of those limits. So it's going to be 1/9 limit as A approaches negative infinity. Okay, then I'm subbing in my 0. So arctan of 1/3 minus, and then I'm subbing in my A, arctan A plus 1/3. Okay, and then plus that other limit, 1/9 limit as B approaches infinity, arctan of B plus 1/3 minus, and then I'm subbing in my 0, arctan of 1/3. Okay, now let's take the limit. So 1/9 arctan 1/3 minus, A is approaching negative infinity, so this becomes, right here, this becomes arctan of negative infinity. The arctan of negative infinity is negative pi over 2, and I've sort of run out of room here, but let me see if I can draw a small sketch. So the graph of arctan x has a horizontal asymptote at y equals pi over 2 and another one at y equals negative pi over 2. And the graph of arctan x looks about like that. So as x approaches negative infinity, arctan x approaches negative pi over 2. So this is going to become negative pi over 2. Plus, and then my next limit, 1/9. And now we have arctan of, right here, we have arctan of infinity, positive infinity. Well, the arctan of infinity is positive pi over 2. Okay, and then minus arctan 1/3. Okay, now distributing our 1/9. 1/9 arctan 1/3 is going to cancel out with the 1/9 times negative arctan 1/3 in the second term here. So that's going to just go away. That one and that one are going to go away. So we have our 1/9 times negative pi over 2. 1/9 times pi over 2. Plus, and then over here we have 1/9 times pi over 2. So we have pi over 18 plus pi over 18 is 2 pi over 18 is pi over 9 for a final answer. 15. Integral of 3 ln 4x over root x dx from 0 to 1. This one looks like integration by parts. U equals ln 4x. dv equals 3 over square root of x dx. So my du, 1 over 4x times 4, or just 1 over x dx. And my v, I'm going to multiply this by 2 over 2, is 6 root x. Okay, so we have 6 root x ln 4x minus integral of v du. So 6, I'll bring on the outside, square root of x times 1 over x is 1 over root x. And I'm going to multiply by 2 here and then multiply by 2 out here. So 6 root x ln 4x minus 12. The integral of 1 over 2 root x is root x. This is a definite integral, so we need to evaluate from 0 to 1. So we have, when we sub in the 1, we have 6 ln 4 minus 12. And when we sub in the 0, we just get 0 minus 0. Okay, so 6 ln 4 minus 12, final answer. Number 16, integral of 3x squared over x minus 1 dx. Now one way to do this problem would be to u-sub, let u equal x minus 1, and then solve your equation, your u equation, solve it for x and square it so you can replace the numerator. Another way to do this problem, if we think about partial fractions maybe, or if you remember when the numerator has a larger degree than the denominator, we can use long division to simplify it. So if 3x squared divided by x minus 1, and that's going to be x. So x squared minus x, then we subtract and we get x plus 1, x minus 1, and we subtract and we get 1. So plus 1 over x minus 1. So this is the same as the integral of x plus 1 plus 1 over x minus 1. And that integrates to x squared over 2 plus x plus ln absolute value x minus 1 plus c. 16. We have the integral of 3x squared over x minus 1 dx. Now you could do this problem with the U-substitution, let u equal x minus 1, solve that equation for x, square it, multiply it by 3, and then you can sub in the numerator. Another way to do this problem, though, is long division. Because the degree on top is higher than the degree on the bottom, we can use long division to rewrite this in a different way. So x times 3x will give me 3x squared minus 3x, and then I subtract that, so I get 3x, and I repeat the algorithm. So plus 3 will give me 3x minus 3, subtract, that's my remainder. Okay, so the integral is equivalent to the integral of 3x plus 3 plus 3 over x minus 1 dx, which integrates to 3x squared over 2 plus 3x plus 3 ln absolute value x minus 1 plus c. 17, integral of x squared plus 2x minus 1 over x cubed minus x. So this one looks like partial fractions. We can factor the denominator. x times x squared minus 1, and x squared minus 1 is x plus 1x minus 1. So we'll set that up as a over x plus b over x plus 1 plus c over x minus 1. And we know that x squared plus 2x minus 1 equals a times x plus 1 times x minus 1. I'm going to put x squared minus 1 plus bx times x minus 1 plus cx times x plus 1. And I'm going to just pick some values for x. I'll let x equal 1. And then I get on the left, 1 plus 2 is 3 minus 1 is 2. On the right, I get a 0 there, a 0 there, 2 times c here. Okay, so that tells me that c equals 1. At x equals negative 1, I get 1 minus 2 minus 1, which is negative 2, equals, that's 0. That's minus b times minus 2 is 2b. And the last term there is 0. So that tells me that b is negative 1. And at x equals 0, on the left we get negative 1 equals. On the right we get negative a plus 0 plus 0. So a equals 1. Okay, so I have 1 over x, negative 1 over b, and 1 over c. So this is equal to the integral of 1 over x minus 1 over x plus 1 plus 1 over x minus 1 dx, which is ln absolute value x minus ln absolute value of x plus 1 plus ln absolute value x minus 1. And we can condense these 3 logs into a single log. So we'll have ln, the positive logs are in the numerator, the negative logs go in the denominator. So x times x minus 1 over x plus 1, still in the absolute value, and then plus c. Number 18, the integral of 2 over x to the 3 halves dx from 1 to infinity. Okay, so this one's already ready to go, ready to integrate. And our discontinuity is at x equals 0, so we don't have to worry about that. Let's go ahead and take our limit as b approaches infinity. And this is the integral of 2x to the negative 3 halves. So when I integrate, I get 2x, negative 3 halves plus 1 is negative 1 half, and then divide by negative 1 half is the same as multiplying by negative 2. And then we evaluate from 1 to b. So limit as b approaches infinity. And I'll sub in the b, so it's negative 4. And the negative 4 actually we can bring out front. Negative 4, like so. Okay, so then it's just, and the x to the negative 1 half is 1 over square root of x. So 1 over square root of b minus 1 over square root of 1, which is just 1. So negative 4, and then let's take the limit. If b is approaching infinity, 1 over the square root of b is approaching 0. So we just get 4. 19. Integral of sine of 2x cosine x dx. Now here we have sine of 2x and cosine of just x. The angles do not match, so we're not going to be able to do a U-sub in the form that it's in right now. We want to use a trig identity on sine 2x so that we have the same angle in all of our trig functions here. So sine of 2x is equal to 2 sine x cosine x, okay, times the cosine x that's already there, gives us 2 times the integral of sine x cosine squared x dx. Now we have an even number of cosines and an odd number of sines. We're going to save the sine for our du and do a U-substitution with u equal to cosine x. Then du is negative sine x dx. So we have 2 integral, and I'm missing my negative for I have my sine x dx, but I need a -1, so I'll multiply by negative. So negative 2 u squared du, and that's just negative 2 u cubed over 3 plus c, which is negative 2/3 cosine cubed x plus c. Number 20, integral of 2x plus 1 over 2x squared plus 3 dx. So this is a tricky one. U-substitution might possibly work, but I don't see a good choice for you, and I don't see something that's going to easily give us a du that we can work with. Integration by parts, probably not going to help too much, because if we let 2x plus 1 be our u, then we're going to have to do, it looks like, maybe an arctangent for our v, and then we would end up having to integrate arctangent. So this one, we want to simplify it. We've got 2 terms in the numerator. Let's try and split this into 2 separate fractions and see if those will be easier to integrate. So this we can rewrite as 2x over 2x squared plus 3 plus 1 over 2x squared plus 3 dx. Now the first integral looks like a u-sub, the second integral looks like an arctan, or a trig sub if you prefer. We'll let u equal 2x squared plus 3, then du equals 4x dx. So I need to multiply the top by 2 here, and then the bottom by 2. That was bad notation. The bottom here by 2. Okay, so I've got the integral of, so the 4x dx becomes du, so it's 1 over 2u du, plus, and then for my second term here, this is going to be an arctan. So we've got root 2x squared plus root 3 squared. And that's going to become 1 over a, so 1 over root 3, arctan u over a, so root 2x over root 3 plus c. And the 1 over 2u becomes 1/2 ln, absolute value of u. Now my u is 2x squared plus 3, which is always positive, so I don't need the absolute value. 2x squared plus 3 plus my 1 over root 3 arctan root 2x over root 3 plus c. Number 21. The question here is, for what values of k is this integral improper? Well, it would be improper wherever we have a discontinuity, or it would be improper if k was approaching infinity. So let's focus on discontinuities. So is there any value of x that would make the denominator 0? And this one, I mean, it kind of jumps out at me right away that you can factor it as x minus 9 and x minus 10. And so if x equals 9 or x equals 10, we're going to have a discontinuity. So it'll be k equals 9 or k equals 10, assuming that k is a real number. So we also would not want k to be approaching infinity. Number 22, find the average value of f of x equals sine cubed x cosine cubed x in the interval from negative pi to pi. We're going to use the average value formula, which is 1 over b minus a times the integral from a to b f of x dx. So 1 over b minus a will be 1 over pi minus negative pi, or 1 over 2 pi. Integral from negative pi to pi, and then we'll integrate our function, sine cubed x cosine cubed x dx. We have an odd number of sines and an odd number of cosines here. So it's our choice whether we want to save a sine or save a cosine. I'm going to let cosine be my u. I'm going to let cosine x be my u. That means I'm going to save a sine. Okay, so 1 over 2 pi, integral negative pi to pi. I'm going to save a sine x, and the other sine squared x, I'm going to convert to 1 minus cosine squared x. Cosine cubed x dx. It's just easier to integrate cosine than it is to integrate sine, which is why I chose that for my u. So if u equals cosine x du equals negative sine x dx, I have the sine x dx but not the negative, so I'm going to multiply by negative negative, and negative 1 over 2 pi. Now my bounds are x values, so I'm just going to use a placeholder here. And this becomes 1 minus u squared times u cubed times du. And that becomes negative 1 over 2 pi from alpha to beta, u cubed minus u to the 5th du. And we're just using power rule there. So u to the 4th over 4 minus u to the 6th over 6 from alpha to beta. And then if I go back in terms of x, u was cosine x, so negative 1 over 2 pi cosine to the 4th x over 4 minus cosine to the 6th x over 6. And now that I'm back in terms of x, I can use negative pi and pi. So first we'll sub in pi. The cosine of pi is negative 1, but we're raising that to the power 4, so it becomes positive 1. And then same with cosine of pi to the power 6, it's going to become a positive 1. Now I'm going to sub in the negative pi. The cosine of negative pi is also negative 1, but we're raising it to the power 4, so we get 1/4. And then same with cosine negative pi to the power 6, it becomes a 1/6. And so we have 1/4 minus 1/6 minus 1/4 minus 1/6, which is just 0, times negative 1 over 2 pi is 0. Number 23. Okay, so we're given an equation, y equals 1 over x squared plus 3x plus 2. And we're told to find the volume of the resulting solid if the region under the curve of this function, y equals 1 over x squared plus 3x plus 2, between x equals 0 and x equals 1, is rotated about the x-axis. Well, I'm looking at this and I notice that it is factorable. We can factor this as x plus 1, x plus 2. Okay, so even without a calculator, I have a sense of what this graph looks like. It has a vertical asymptote at negative 1. It has a vertical asymptote at negative 2. Okay, so vertical asymptote here, here. It has a horizontal asymptote at y equals 0. What else do we know? And it's only asking us to find the volume of the region between x equals 0 and 1. So I'm really only interested in what's happening first quadrant. I'm guessing that the graph is like decreasing and following these two asymptotes up here. we can plot a couple points to check. So let's see, when x is 0. When x is 0, I'm looking at the original equation. When x is 0, y is 1/2. Okay, so I'll just say 1/2 is like right there. And then when x is 1, we get 1 over 1 plus 3 plus 2, 1/6. So it is decreasing, and it's approaching this asymptote. Okay, so maybe a better picture so we can see what's going on. We've got our y-intercept here at 1/2, and the graph is coming down like this, approaching that asymptote, and our region just goes from 0 to 1 there. Okay, so we want to rotate this around the x-axis. So it makes sense to set this up using a vertical rectangle, making this a dx problem. And our equation is in the form of y equals a function of x, so this will be easy to do as a dx problem. Our volume formula, this is disk method, it's just going to be pi times the integral from 0 to 1 of our radius squared. And our radius is this vertical distance right here. Top minus bottom is just the function minus 0. Okay, so this is our function right here in factored form, and that's our radius. We want to square that. So it'll be 1 over x plus 1 squared, x plus 2 squared dx. Now to integrate that, we're going to use partial fractions. So this is going to be a long one because we'll need 4 fractions here. We're going to need an a over x plus 1, a b over x plus 1 squared, a c over x plus 2, and a d over x plus 2 squared. Okay, so we have 1 equals a times, so my least common denominator here, my LCD, is what I have right here. So the a only has an x plus 1, it still needs another x plus 1, and it needs the x plus 2 squared. Plus b, the b already has an x plus 1 squared, it just needs the x plus 2 squared. Plus c has an x plus 2, it needs another x plus 2, and the x plus 1 squared. Plus d already has x plus 2 squared, it needs the x plus 1 squared. Okay, and we want to solve for our coefficients, so I'm just going to say at x equals -1, my equation becomes 1 equals, first term is 0, second term is, let's see, when x equals -1, the second term is just b. The third term is 0, the fourth term is 0. Okay, so that's nice. We immediately found the value of b. So I am going to go ahead and replace b with a 1. Make it a little easier to solve for the others. Okay, at x equals -2, we get 1 equals, first term is 0, next term is 0, next term is 0, and x is -2 here, so we just get d. Oh, that's nice. So I also know that d is 1. And we still need to solve for a and c. So I've run out of convenient x values to use. Let me just use x equals 0. At x equals 0, the equation becomes 1 equals a times 1 times 4. So 4a. And then x is 0, so plus 4. And then 2 times 1 times c, so plus 2c, plus 1. Okay, so I'll just simplify that a little bit. 4a plus 2c, and then I'll subtract 5, so that equals -4. Okay, I have two unknowns, so I'm going to need to get another equation to solve, and then we'll solve the system. So let's say at x equals 1. At x equals 1, I get 1 equals, okay, if x is 1, this is going to be 2 times 3 squared, so 18a. 18a. The next term when x is 1 is going to be 9. The next term when x is 1 is going to be 3 times 2 squared. 3 times 4 is 12. So 12c. And the last term when x is 1 is going to be 4. Okay, so 18a plus 12c plus 13. I'm going to subtract the 13. So equals negative 12. Now this equation I'm going to multiply by negative 6. So I'll have negative 24a, negative 12c. I'm multiplying by negative 6, so equals 24, and then I'm going to add these equations together. So I get negative 6a equals 12, a equals negative 2. A equals negative 2. And if a is negative 2, I can come back to this equation and solve for c. 4 times negative 2 is negative 8, plus 2c equals negative 4. Add 8 to the other side, we get 2c equals 4. Then c equals 2. c equals 2. Okay, so now I can put in my coefficients. So I have the integral, pi times the integral from 0 to 1 of negative 2 over x plus 1 plus 1 over x plus 1 squared plus 2 over x plus 2 plus 1 over x plus 2 squared equals pi. Let's integrate. So negative 2 ln absolute value x plus 1. 1 over x plus 1 squared, we can think of that as x plus 1 to the power negative 2 and integrate. So we have x plus 1 to the negative 1 times negative 1. So negative 1 over x plus 1. Okay, plus 2 ln absolute value x plus 2, and then minus 1 over x plus 2, and we need to evaluate this from 0 to 1. So first we will sub in 1, we get negative 2 ln 2 minus 1 over 2 plus 2 ln 3 minus 1 over 3. Okay, and then we're going to subtract, sub in 0, negative 2 ln 1 minus 1 plus 2 ln 2 minus 1 over 2. Let me distribute, okay, that negative, so pi times negative 2 ln 2 minus 1/2 plus 2 ln 3 minus 1/3 plus 2 ln 1. Well, natural log of 1 is 0, so that's gone. Plus 1 minus 2 ln 2 plus 1 minus 2 ln 2 plus 1/2. Okay, minus 1/2 plus 1/2, that's 0. And we have 1 minus 1/3, that's 2/3. And our logs, we've got minus 2 ln 2 minus 2 ln 2, that's minus 4 ln 2, plus 2 ln 3. Okay, almost there. 2/3. Minus 4 ln 2 is minus ln 2 to the 4th, which is 16, plus 2 ln 3, that's ln 3 squared, that's ln 9. Okay, pi, and then 2/3 minus ln 16 plus ln 9, that's ln 9 over 16. Number 24, write an integral to represent the arc length of the function f of x equals x cubed plus 2 from x equals 1 to x equals 3. Well, our arc length formula says we integrate on our interval, so from 1 to 3, the square root of 1 plus f prime squared. So f prime of x is 3x squared dx. And that's all there is to that. We're not asked to evaluate it, just to set it up. And 25. The length of a curve from x equals 1 to x equals 5 is given by the integral from 1 to 5, the square root of 1 plus 36x to the 4th dx. If the curve contains the point 1, 9, write a possible equation of the curve. Well, if this is the arc length, then we know that the derivative squared, y prime squared, equals 36x to the 4th. And that tells us that y prime is 6x squared, or I guess possibly negative 6x squared. But it does say write a possible equation, so it's possible that y prime is 6x squared. And we're looking for y, not y prime, so we would want to integrate this. And the integral of 6x squared would be 6x to the 3rd over 3 plus c, or 2x cubed. Yeah, 2x cubed plus c for our y. And then we know the function passes through the point 1, 9, so 9 equals 2 plus c, and that means c equals 7. So y equals 2x cubed plus 7. And that is the end of our review of advanced integration techniques.